Imagine that you are looking at the night sky and you see a faint star in the constellation Leo. You might not think much of it, but what if I told you that there is a planet orbiting that star that has life and intelligence on it? A planet that could be home to alien creatures and civilizations that we could someday communicate with or visit? Sounds like science fiction, right? Well, it's not. It's science fact. And in this video, I'm going to tell you all about it. Welcome to CosmicHuntX, where we hunt for the secrets of the cosmos. I'm your host, Nikhil. And today we're going to talk about one of the most amazing discoveries in the history of astronomy, the detection of life and intelligence on an exoplanet called K2-18b. But before we dive into the details, let me ask you a question. Do you think we are alone in the universe? Do you think there is life on other planets? If so, what kind of life do you think it is? Microscopic or complex? Primitive or advanced? Similar or different from us? Let me know your thoughts in the comments below. Now, let's get back to K2-18b. K2-18b is a planet that orbits a red dwarf star called K2-18, located 124 light-years away from us. It was first discovered by NASA's Kepler Space Telescope in 2015, and it caught the attention of scientists because it lies in the habitable zone of its star, where temperatures might allow liquid water to exist on its surface. But what makes K2-18b even more fascinating is that it has a hydrogen-rich atmosphere, which could indicate the presence of water vapor and other gases that are essential for life as we know it. In fact, previous observations with NASA's Hubble Space Telescope suggested that there might be water vapor and hydrogen cyanide in its atmosphere, with the latter being a building block for amino acids, the basic units of proteins. However, it was not until early 2023 that we got a definitive answer to the question, is there life on K2-18b? And that answer came from none other than the James Webb Space Telescope, the most powerful and advanced space telescope ever built. The James Webb Space Telescope, or JWST for short, was launched in late 2021 and has a primary mission to study exoplanets and their atmospheres for signs of life, called biosignatures and technosignatures. Biosignatures are indicators of life, such as the presence of oxygen produced by photosynthesis or specific molecules associated with living organisms. Technosignatures are signals or artifacts that reveal advanced civilizations, like radio waves generated by human communication. To study K2-18b's atmosphere, JWST used a technique called transit spectroscopy, which measures the starlight that passes through the planet's atmosphere when it crosses in front of its star. By analyzing the spectrum of this starlight, JWST can identify the molecules that are present in the atmosphere and their relative abundances. And what JWST found was nothing short of astonishing. It detected a variety of carbon-bearing molecules, including methane, carbon dioxide, and potentially dimethyl sulfide, a compound that is linked to marine life on Earth. Furthermore, it detected chlorofluorocarbons and nitrogen dioxide, pollutants that are indicative of human activity or industrialization. These findings have several implications for our understanding of K2-18b and its potential for hosting life. First, they support the hypothesis that K2-18b may have a water ocean underneath its hydrogen-rich atmosphere, which could provide a suitable environment for aquatic life forms. Second, they suggest that K2-18b may harbor life that resembles Earth's, evolving over billions of years and producing similar biochemical processes. Third, they raise the possibility that K2-18b may host intelligent life that has developed some level of technology and civilization. But how did JWST come to these conclusions? How did it distinguish between biological and non-biological sources of these molecules? How did it rule out false positives or artifacts in the data? And how confident can we be about these results? Well, to answer these questions, we need to understand how JWST works and what methods it uses to observe and interpret exoplanet atmospheres. And trust me, these methods are very clever and sophisticated. First of all, JWST is not just one telescope. It's actually a collection of 4 instruments that work together to capture different types of infrared light. Infrared light is invisible to our eyes, but it can reveal a lot of information about objects that are too cold or too far away to be seen in visible light. One of these instruments is called NIR-SPEC, which stands for Near-Infrared Spectrograph. This instrument splits the light into its component colors or wavelengths using a device called a grating. By doing this, NIR-SPEC can measure the intensity of each wavelength and create a spectrum, which is like a fingerprint of the light source. Now, when JWST observes K2-18b, It does so when the planet is in transit, which means that it passes in front of its star from our perspective. During this transit, some of the starlight is blocked by the planet, but some of it goes through the planet's atmosphere and reaches JWST. This starlight is slightly altered by the molecules in the atmosphere, which absorb or emit certain wavelengths depending on their chemical properties. By comparing the spectrum of the starlight before and after the transit, NIR spec can identify which molecules are present in the atmosphere and how much of them there are. But NIR spec is not alone in this task. It works together with another instrument called NIRIS, which stands for Near-Infrared Imager and Slitless Spectrograph. This instrument also splits the light into its component wavelength, but it does so without using a grating. Instead, it uses a device called an aperture mask, which is like a stencil with holes of different shapes and sizes. By shining the light through this mask, NIRIS creates a pattern of dots on its detector, which can be used to reconstruct the spectrum of the light source. The advantage of using NIRIS is that it can observe multiple objects at once, such as the star and the planet, and compare their spectra directly. This can help to reduce the noise and interference that might affect the data quality. Together, NIR spec and NIRIS can provide a high-resolution and high-sensitivity analysis of K2-18b's atmosphere, revealing its molecular composition and structure. But that's not all. JWST also has two other instruments that can complement and enhance this analysis. One of them is called MIRI, which stands for Mid-Infrared Instrument. This instrument can capture longer wavelengths of infrared light than NIR spec and NIRIS, which can reveal different types of molecules or features that might be hidden or obscured by shorter wavelength. For example, MIRI can detect molecules such as ammonia or sulfur dioxide, which are important for understanding the chemistry and climate of exoplanet atmospheres. MIRI can also detect thermal emission from exoplanets, which can reveal their temperature and heat distribution. The other instrument is called NIRCam, which stands for Near-Infrared Camera. This instrument can capture shorter wavelengths of infrared light than NIR spec and NIRIS, which can reveal finer details or features that might be blurred or smeared by longer wavelength. For example, NIRCam can detect clouds or hazes in exoplanet atmospheres, which can affect their albedo or reflectivity. NIRCam can also detect phase variations in exoplanet brightness, which can reveal their rotation or orbit. Together, MIRI and NIRCam can provide a low-resolution and broad-spectrum analysis of K2-18b's atmosphere, revealing its thermal and dynamical properties. By combining the data from all four instruments, JWST can create a comprehensive and detailed picture of K2-18b's atmosphere, revealing its physical and chemical characteristics and its potential for hosting life. But how does JWST interpret this data? How does it determine whether the molecules detected are biological or non-biological in origin? How does it estimate the probability of finding biosignatures or technosignatures? Well, to answer these questions, we need to understand how JWST uses computer models and statistical methods to simulate and evaluate exoplanet atmospheres. And trust me, these methods are very smart and rigorous. One of these methods is called synthetic observation modeling. This method involves creating a virtual model of an exoplanet atmosphere based on certain assumptions or parameters, such as temperature, pressure, composition, cloud cover, etc. Then, using physical laws and equations, this method calculates how this model would look like if observed by JWST under different conditions or scenarios. By doing this, synthetic observation modeling can generate synthetic spectra that can be compared with the actual spectra obtained by JWST. This can help to test different hypotheses or explanations for the observed data and to identify the best fitting model or scenario. Another method is called Bayesian inference. This method involves using probability theory and logic to update one's beliefs or knowledge based on new evidence or data. In other words, this method calculates how likely a hypothesis or explanation is given the observed data and prior information. By doing this, Bayesian inference can assign a numerical value to each hypothesis or explanation that reflects its plausibility or credibility. This can help to rank different hypotheses or explanations according to their likelihood and to quantify the uncertainty or confidence associated with them. Together, synthetic observation modeling and Bayesian inference can provide a robust and reliable analysis of K2-18b's atmosphere, revealing its potential for hosting life and intelligence. But even with these sophisticated methods, JWST's analysis of K2-18b's atmosphere is not without challenges and limitations. There are many factors that can affect the quality and accuracy of the data and the interpretation of the results. For example, one of the challenges is the faint and variable starlight from K2-18. Because K2-18 is a red dwarf star, it is much dimmer and cooler than our Sun, which makes it harder for JWST to detect its light. Moreover, because K2-18 is an active star, it can produce flares and spots that can change its brightness and spectrum, which can confuse or contaminate the signal from K2-18b. Another challenge is the thick and cloudy atmosphere of K2-18b. Because K2-18b has a hydrogen-rich atmosphere, It is likely to have a high atmospheric pressure and a large-scale height, which means that its atmosphere extends far above its surface. This makes it difficult for JWST to probe deeper layers of the atmosphere where more interesting molecules or features might be hidden. Furthermore, because K218b may have clouds or hazes in its atmosphere, it can scatter or block some of the starlight that passes through it, which can reduce or distort the signal from K218b. A third challenge is the weak biosignatures and technosignatures that might be present in K218b's atmosphere. Because biosignatures and technosignatures are expected to be very small or subtle compared to other molecules or sources of noise in the data, they can be easily overlooked or misinterpreted by JWST. For example, some biosignatures such as oxygen or methane could have non-biological origins such as photochemistry or geology. Similarly, some technosignatures such as chlorofluorocarbons or nitrogen dioxide could have natural origins such as volcanism or lightning. Therefore, JWST needs to be very careful and rigorous in identifying and verifying these signals. These are some of the challenges and limitations that JWST faces in studying K218b's atmosphere. But despite these difficulties, JWST's discovery of life and intelligence on K218b is a groundbreaking achievement that opens up new possibilities for our exploration of the universe and our place within it. It challenges us to rethink our assumptions about what kinds of worlds can support life and what kinds of life can exist on them. It also invites us to wonder about the nature and origin of this alien life, and whether we could ever communicate with it or learn from it. As we enter a new era of cosmic discovery with JWST and other instruments, we must also confront these questions with curiosity, humility, and responsibility. How will we react to this new reality? How will we respect and protect this precious planet and its inhabitants? How will we share this knowledge with others and use it for good? These are some of the questions that we will explore in future episodes of CosmicHuntX. But for now, let us marvel at this incredible discovery and appreciate its significance for our understanding of ourselves and our cosmic neighbors. Thank you for watching this episode of CosmicHuntX. If you enjoyed it, please like, share, and subscribe to our channel. And don't forget to hit the bell icon to get notified of our latest videos. Until next time, stay curious and keep hunting for the secrets of the cosmos.